welcome back to quantum computing. In case anyone is wondering why I constantly wear my AirPods, it's not that I'm listening to music all the time. It is because the microphones are just better than the microphones in my computer. So that's why I'm here with AirPods. Anyway, so today's lecture is about vector spaces and linear algebra, some notation that we need for quantum computing, some explanation as to what the Dirac notation is. We will go into more detail with that. I know we talked about it last time already. We will go a little more in depth with transformations that we want to understand and how to execute, and also what it means to represent a quantum bit. It's not only that we have one way of representing a quantum bit, there are multiple ways. If you feel comfortable with linear algebra and vector spaces, you don't need to listen to this lecture, so it's perfectly fine if you skip it. But if you feel you need a refresher, then you're most welcome to stay, of course. Let's look at the basic properties and Dirac notation. That's where we start, basic properties of the vector spaces. So in quantum computing, integers from 0 to n are associated with n plus 1 orthogonal unit vectors in a vector space of d equals n plus 1 dimensions over complex numbers. What does that mean? So that means, remember when we talked about single qubit states, then you remember the state 0, and you also remember the state 1. So these are the simplest systems that we can look at in terms of quantum computing. Then these are the basis vectors that are given. However, associated with each basis vector, so let's write it down in vectorial form, 1, 0, 0, 1. Associated with each of these basis vectors, you have a probability amplitude. This probability amplitude gives you the probability of this state that you have in a system of collapsing into whatever subsystem it is. I think it becomes more clear if I write down a superposition state. Remember, we talked about the Hadamard transformation briefly already. When we look at a state like this, for example, this is an equally weighted superposition of these two basis states of 0 and 1. So the basis states are definite. There is no probability. But for superposition states, we have probability amplitudes. And remember, you get the probability if you square the amplitudes. Why is that? Because our probability amplitudes are complex numbers. And anytime you square a complex number, you get a real number. And that's the probability associated with each of the states. Equally weighted in that case means that there is the same probability for the state to collapse into 0 or into 1. So depending on how you look at the system, depending on how you look at the system, when you look at the system, you cannot say in advance, in this case, if the system will collapse into 0 or 1. So what is the final output, the remainder of the state? Remember, because when you have a superposition, you have all these rich probability amplitudes, so all possible combinations, linear combinations of states, but when you look at the system, you lose all that. You will end up with a definite state. And we do our transformations, we do our evolution of the system on the superposition state. That's one reason for the incredible power of quantum computers, because you can run operations on all possible configurations of the systems at once. Okay. Orthonormal vectors may be denoted by, as I said here, phi 1, phi 2, and so on, with a subscript. And orthonormal, remember, we're dealing with normal vectors or unit vectors. So that means the length of the vector is 1. So that generalizes to higher dimensions. If you have 2-dimensional qubit space, remember you have 4-dimensional vector space. In the case of 0, 0, you may see something like that. And this is still a unit vector. So the next thing is that they are orthogonal. So orthogonal means that they're perpendicular to each other, as you can see in that graphic in the slide. This is necessary because we want to be able to distinguish our states appropriately. We have to have orthogonal vectors and we have to have unit vectors. Let me give you an example in bracket notation or Dirac notation. So I may mix it. I may sometimes say bracket notation. I may sometimes say Dirac notation. That's the same. Paul Dirac invented bracket notation. If we look at, just want to check if these vectors or this basis here fulfills this requirement. That they are, so of course they fulfill the requirement of unit length, but then are they orthogonal? So let's check. For this, we take the bra. You remember the bra is the row vector of an associated ket. So this is the ket vector. The bra, in that case, for 0 would be 0. And let's just see if this is orthogonal to this one here, which is 1. So we take the inner product, and in that case, we know the bra is a row vector. So that looks like that. And then we have our ket vector here, which is a column vector. In that case, 1. Let's execute that multiplication and see 1 times 0 plus 0 times 1 equals 0. Orthogonal. Perfect. And the other requirement that we have is, when you look at it, if you take the inner product with a vector itself, then the result must be 1. And let's see. Let's again take 1, 0 times 1, 0. And I do 1 times 1 plus 0 times 0 equals 1. Perfect. Requirement fulfilled. Yes, I just said that unit vector is a normed vector, length 1. What you see here is a representation of vector on a sphere. We also sometimes represent qubits or qubit states on a sphere. It's called the block sphere, where you have, so we'll look into more detail into the block sphere later. But of course, you have 3 axes because it's a sphere, so it's 3-dimensional. And every qubit state, so also the superposition states, can be represented on the surface of that sphere somewhere. So in theory, that gives you an infinite number of potential states. However, in reality, we're dealing with a finite number. Also, in theory, there is an infinite number of unitary transformations that you can execute, but also we only use a limited subset. Unit vectors may be used to represent the axes of a Cartesian coordinate system. So for example, the direction x, y, and z of a 3-dimensional coordinate system can be given by these 3 vectors that you can see here. For x, we take, of course, 1, 0, 0. For y, we take 0, 1, 0. And for z, we take 0, 0, 1. We just proved here with a simple example how orthogonality and normalization conditions are expressed. And let's continue with the formalism. So, indices, as we wrote them down here, can be used for describing these state vectors. However, it may just be easier to use the indices directly. So let's say instead of using 1 here, we write 1. If we have a bigger one, let's say a 2-qubit state, then we might write it down as this one here. You can give this any name. However, in quantum computing, normally people give it the numbers of the vectors. So if we have a 2-dimensional 0, 0 space, remember that's that space here, so you just write it down here. However, it can become tedious if you have hundreds of bits all of a sudden. We don't have a quantum computer, or actually we have quantum healing systems, but that can represent longer bit vectors. But if you have in the future, you have hundreds of bits here, then you will probably not write down all hundreds and create super long vectors or descriptions of these vectors. So instead, you may decide that in that case here, this one is given by 0. Then you have maybe another one, which is given by 0, 1, 1, 0. That could be represented by 1, and so on. To denote in which dimension we are, so because this can be, of course, 3, 4, 5-dimensional. So here we say it's 2-dimensional qubit space. You might give it a subscript here and say it's 2 dimensions. Okay. Yes, we had that example here, the very simple example with the linear combination. What that means is that for every possible state that a system can assume, for every possible solution to your problem, you have a probability of the system collapsing into that. And it's not always like we have it here, an equally weighted superposition that wouldn't do us any good, because then all the outcomes of my computation would always be random. So anytime I look at the system, I have, in that case, a 50-50 chance of measuring that and that. Or in two-dimensional space, it's a 25% chance of measuring either that or that one or the other two states. So therefore, very often we have different probability amplitudes for each of the states. And that's actually the whole artistry of gate model quantum computing. So once you have a quantum computer, of course, but the whole artistry is to make sure that you manipulate this probability amplitude such that once you look at the system, which means you make the measurement, that once you look at that system, you get the required outcome, the desired outcome. So what do you want? The solution to a problem, or maybe learn something about your problem. So if you formulate your problem correctly, or the evolution correctly. We also remember that the coefficients usually are taken, so not usually, they are taken from the complex numbers. And complex numbers, if you square them, then you will get a real number. And the real number gives you the probability of a state collapsing, so of a system collapsing into that state. So that we just had before. Just an additional excursus on linear combination. What you keep in mind about linear combination is that every possible configuration of the system, so that the system can collapse into, associated with a probability amplitude, that in the form of that plus the other one, plus the states here, that gives you, or that is the linear combination of the system. So for each of these, if we look at that example down here, for each of these, you have the probability amplitudes. Here we chose an equally weighted superposition. Here we have a superposition with different amplitudes. Here we have alpha for state 0 and beta for state 1. And that just means you can write it down as the wave function in the form of, in a vectorial form with alpha and beta here, because you know if you multiply alpha times 0 times that vector, then the result is alpha on that position. Same for beta, so beta is down here. And this is equivalent to the example that we have in the slides here with Euclidean space, where you have the constants a1, a2, a3 that you can either have in the vectors or move out of the vector and use your basis vectors and multiply it with your basis vector and make this linear combination that I just mentioned. That means every possible state can be represented as a linear combination of all the basis states. Okay. Remember the complex conjugation too. So if you look at a complex number here, like this one here, Z, we call it U plus IB, or we give it U plus IB. And here the complex conjugate just switches the sign. So in that case, you would have U minus BI, okay? We talked about the complex conjugate before when we talked about Hermitian operators, the allowed transformations that you can use in quantum computing. So remember, when you have an Hermitian operator, that means you take the original operator and multiply it with the complex conjugate transpose, which was that dagger notation. You remember that too. And if the result is identity, then you have an allowed transformation in quantum computing. That means the transformation preserves the unity of the vector space. So you want to make sure that every transformation you execute also preserves the unity. The inner product is linear on the right-hand vector, as the example in the slides shows, and anti-linear in the left-hand vector. I'll leave that to you to read through that, but it's fairly straightforward. Okay. We talked about orthonormality already. Yes, so in terms of how you make an inner product, we also looked at that. Here it's just the probability amplitudes that we would use. So in that case, if we want to do an inner product, we would use the complex conjugate the complex conjugate for a complex number here. In that case, it's given by alpha, which is your row vector here, right? So it would be a row vector with amplitudes, whatever. But then also multiplied by the column vector. So the row vector gives you the complex conjugate, or in the row vector, you need to use the complex conjugate and multiply it by the column vector amplitudes. And one thing that we also want to still remember is that all the amplitudes must square to unity. So you cannot have a system with amplitudes that go over unity or under unity, so it must square to unity. So that's one of the requirements, because we want to make sure that with a definite probability, we can get each of the states that we measure or that we have in the system once we measure the system. Here is the transformations that we just mentioned before. This is just the linearity rule that we discussed before. So if you have a transformation, give it a capital A here, and you have a state. So then if you multiply that state or execute the transformation on that state, then it means, of course, it's executed on both. We talked about the inner product. Another example that you see here in the slides is an outer product that's sometimes also used to, or actually it is used to create operations. So execute operations or operations they can execute. So let's say I want to have a projection operator on the state 0. I would write that in that form here. So instead of the inner product, I now have the outer product. And let's look at what that means. So in that case, I start with the column vector here, and I get the row vector here, which is 0, 1. And I do, oh, sorry, it's a writing mistake. It's 1, 0. So I do 1 times 1. In that case, is on this position here. I do 1 times 0, 0 times 1, and 0 times 0 gives me that one here. And the interesting thing is, so let's say I want to make a transition or a transformation that takes that state into that state, so leaves it as it is. It's just another example. And also takes that state and leaves it as it is. So we just execute that one, which is 0, 1 times 0, 1, which gives me 0, 0, 0, 1. So if you add these two up, the interesting thing is you get the identity transformation. So this transformation leaves each of the states, 1 qubit states, in the same state, leaves it alone. So this is how you can create transformations. We will learn about that in more detail later, but just so you know, this is how you can come up with transformations. So the unitary transformation, to sum that up, it preserves the magnitudes of all the vectors. So a unity vector, or a unit vector, sorry, is a vector of magnitude 1, and must preserve not only inner products of arbitrary vectors with themselves, but also inner products of arbitrary pairs of vectors. Linearity is what it's called. We had a look at that before. No key messages left. There's additional notation. Let's also skip over that. So we just remember the ket is the vector in the original space, and the bra is the vector in dual space. And so if you take the amplitudes, the probability amplitudes, then you see in the dual space, in the bra space, you see the complex conjugate, whereas in the original vector, you see the original complex number that you have. Still, the basis vector changes from column vector to row vector. So if you take a bra as initial vector, you have a column vector. If you take the ket, it is a row vector, right? As we saw here. Where here we have an example here. Here we have the bra as a row vector and the ket as a column vector. Let's look at an example. I would want to say it's a more practical example. Still not as practical as it will get in that course, but it is something we can work with. So in quantum physics, as we just learned, the probabilities, or more precisely the probability amplitudes replace the absolute measurement values. Let's assume we have two dices. So in two dice, and we want to throw these dice and look at the possible outcomes. So the possible outcomes, you don't see one here, because if you have two dice, the smallest number you can get is 2. Okay, so it's 2 times 1. So you have the sum of the i's, 2 to 12 here. So, and then we look at how often can we get each of these results with different combinations. So if we look at each die independently. So then the thing is that the highest one, if we look at 7 here, is 7. So there are most combinations of die, so when I throw them, give me 7. So this is then the most likely outcome that I get when I throw the dice, right? So let's move on. Give me a second. So let's look at the probabilities classically. We look on the left-hand side, you see the probabilities. So that so when you look at the sum of all these here, it's 36. So it's therefore, in that case, since you get one combination, so which is 2 ones only, give you 2, you have 1 in 36. So 1 over 36 is your probability here. And here you have the probability amplitudes. So which is, remember, the squared probability amplitude is the probability. So in that case, we just take the root because we start with the probabilities, and I have 1 over 6 because 6 times 6 is 36. So here also, we have 2 to the power of 1/2, which equals the square root of 2. Okay, so and so on. Here for 4, we take the square root, we got 2. So therefore, still we see the highest probability with the number 7. So instead, and we moved on. We have now inevitable dimensional space. We're not dealing with 1 or 2 dimensional spaces anymore. Usually, the components are composed of functions, and still we have the same requirement. The functions need to be linearly independent. So remember, linear combination. Linearly independent means that they're independent axes. And since we're dealing with complex numbers, it's independent axes in Hilbert space. And here you see an example. So when we take our complex number, so we add a function here. Same. For any ket vector, there is a bra vector. Yeah, we started with the ket vector again, which is our column vector, and now we want to do the row vector. In that case, you see the row vector here, which is just the transformation. Okay, so that all the same. We all know that already. You can, if you want, you can try if it's normalized. I would be surprised if it wouldn't be the case, but if you get another result, let me know. So remember, before we talked about, briefly talked about this transition from position into momentum space. That's one of the reasons why we want to do a symbolic calculation. So symbolic calculation is what we saw, notation by Dirac, without being restricted to a basis. And so here you see some reasons. So let's say we start out with momentum space, or want to start in position space, and I want to end up in momentum space. Then any position vector, if you would do or avoid symbolic calculation, then you would have to do the transformations during the calculation. But actually, we don't want to do it during the calculation. We want to get the result after it. So that's not so much relevant for quantum computing. That's quantum physics in general. But just so you know why we use Dirac notation. So on the one hand, it's more convenient. That's actually the best reason for it for now. And it makes, so by just writing it down, and it makes it easier to execute computations or to run your algorithms. Yes, that just adds to what I said. We had that example before. So when you look the bottom of that slide, then we talk about orthonormality. If, let's say we have these two states here, if you take the two and I do an inner product, the result is 0. So it would also be 0 if I take 1 here and 0 here. And for both of them, for 0, 0 and for 1, 1 in that case, I would have the requirement that the result would be 1. So then if that's true for both or for all the states, so if you have bigger systems or bigger basis states, state space, then you are or can make sure that the states are orthonormal, which is the requirement. Measurement parameters in quantum physics are generally represented by or in the form of operators. An operator applied to a wave function. So remember, in that case, we talked about the wave function. This is the wave function, the probability amplitudes here. An operator applied on a wave function creates a new wave function. Here we have an example. We have an impulse operator. That's not something we need in quantum computing. It's just a quantum physical operator. Then we have another operator that's well known, the operator for kinetic energy. So we have the classical one. You see in quantum physics, it becomes h bar squared or negative h bar squared over 2 times the mass times the Laplace operator. So Laplace operator is the second degree gradient that we will have a look at that in a moment. And h bar squared, so h bar is the reduced Planck's constant. That just, so it means the original Planck's constant, h, divided by 2 pi. And that gives you a result in atomic units. So that's why we use that as one atomic unit. And the Hamilton operator, so it's not what we saw with the Hadamard transformation. The Hadamard transformation is also denoted by H. So a Hamiltonian or Hamilton operator in that case describes in a matrix form the overall energy of a quantum mechanical system. So the Hamiltonian applied to a wave function equals the energy of the wave function. So it gives you the energy of the wave function. And you may have heard about that very famous equation. This is the Schrödinger equation. It's different for any quantum mechanical system and very complex. So even if you have small systems, it's very complex to run this Schrödinger equation and impossible in most of the cases. So we need to do approximations. If we want to do a simulation of a molecule, for example, we don't have exact simulations. This is also why we are very interested in quantum computers, because the promise of quantum computers is that we can, at some point, when we have big enough chips, at some point simulate molecules of industrial relevancy, and so find new materials, improve battery chemistry, whatever you're interested in. There is the unity operator. Here we talked about the identity operator before, which I showed you here. This just leaves a state unchanged, a ket unchanged. You may wonder, why do I even need that? Because if I do nothing to it, I may as well just do nothing instead of applying an identity operator. Well, that's not exactly true. If you have a 2-qubit state, for example, here, and you only want to manipulate the second one, you want to apply a NOT operation to that one here, for example, then you can't just apply, how would you do that? A NOT operation, so which is in that case, remember, it's 2-dimensional, however, this is 4-dimensional vectorial space. So how would you apply it to that? So what you need to do is consider, in that case, an identity transformation, which leaves the first state or the first qubit value alone. So apply identity to the first one and not to the second one. And remember, if we want to create a 2-qubit transformation, we always have the way of the tensor product. So we take our identity here, leave the first state alone, and create a tensor product with the NOT operation that we have here, and then you will have a 4-dimensional 2-qubit operator. That generalizes to bigger systems, of course. So yeah, we described the kinetic energy of a particle, a momentum operator. And the Schrödinger equation, here is just a re-expression of the Schrödinger equation in terms of the outer potential and potential energy. And kinetic energy, and you see the Laplace operator that I just mentioned before. Okay. So the gradient, remember the gradient gives you, so it's not a derivative, but the gradient gives you the slope for each of the directions. So a partial derivative, as you can see here, for the x, y, and z direction. Then we have the impulse operator as another example. These are, so I will go over these rather quickly because we don't need them for quantum computing, but I want you to know there are other operators than the ones we will learn about for quantum computers in quantum physics, something that people work with, okay? And operators, as I remember, I think I mentioned that in my first or second lecture, are not commutative, so which means the sequence sometimes matters. So sometimes operators do commute, sometimes they don't. If you want to find out, then you do as shown here. If A, so if you have two operators, A, B, means two matrices. If that doesn't equal BA, then you know they don't commute. So therefore the sequence matters. If I apply A before B or B before A is relevant. I can't just do as I please. Yes, we have linearity again. So an operator is linear if in that example, you see you have a qubit state, you have two constants, C1 and C2, and you apply the operator A on it, then it applies, of course, to the whole state. It doesn't only apply to the first or second one. We briefly talked about that already. So the Hermitian, as you remember, is you take the complex conjugate transpose of an operator. The complex conjugate is switching the sign of complex numbers of the complex part of the complex number, and taking the transpose is flipping it around the diagonal, right? The diagonal. So you just leave the values on the diagonal and you flip around the diagonal. Here, another interesting thing to know and to understand is when you look at the of two states. So let's say you want to calculate the expectation value of something. So we'll look at that later. Of the same state for the dice operator, then we would take, of course, one ket vector and just take the bra. But here we have different systems. So we have the system phi and the system psi. And you see the operator here in the middle. If you flip it around, so take instead of bra phi, you take bra psi, and instead of ket psi, you take ket phi, and add the Hermitian, so the complex conjugate transpose in the middle, then you would get the same result. So this is identical. Let's look at the expectation value. This is what I mentioned before. So the expectation value, very simple, is the most likely outcome. So what you can expect when you measure a system. And let's look at it for the dice operator. For the dice operator, as you remember, we have 12, actually 11 possible outcomes. So when you throw dice, two dice, then on the upper left side, you see the number 2. So this is 2 times 1, right? Number 3, 4, 5 until 12. So we represent this in a matrix. And the dice operator therefore stores all the possible values that you can get with your dice. But then still we have the probability amplitudes, and we want to make sure, or we want to calculate the expectation value. So what's the most likely outcome? So remember, when we looked at it, this is a very simple system. The most likely result or probable result that you get is the number 7. The number 7, if we want to verify that with our probability amplitudes here, we take the bra, which is the row vector of our probabilities, and we have the ket here, and in the middle we have our operator. And we execute that multiplication. And you see the result is 7. So the most likely outcome is 7. Interesting. So that's how you get your expectation value. And I know the dice operator, so this is not something that you may relate to any practical problem, but imagine just I want to find out on all possible configurations at once. So all the possible combination of dice I can throw, what's the most likely outcome? Then you can do it with a quantum computer. We have some more rules here when it comes to transformations and vectors. Just remember that if you, so that some are just notation things. So if you have a, there's a constant multiplied by a, the big A, capital A, an operator, and you take the complex conjugate transpose, then for the constant, since it's a complex number, you won't take a transpose, but you will take the complex conjugate. Okay, you see the complex conjugate times that operator, complex conjugate transpose of the operator is the same as if you take the complex conjugate of everything. And some more rules. So I encourage you to read through that, and please get back to me if you have questions. It's just something that we want to memorize, or you have on some or in some sheets with formulas so that you can take to the exam. Some more, please read through that. So I think you can read through that on your own. Hermitian operators, there's some more things to know. Yes, these are just rules, so please go over that yourself and ask me if you have questions. Okay. We also talked about the outer product already. Projection operator, we briefly talked about that. So if you want to project onto 0, for example, if you take that one, that gives you the projection operator. So with your two vectors, you have 1, 0, 1, 0. That's how you create the projection operator. It projects on 0. Same for 1. It projects on 1, on the state 1. That's how you create it. Okay. This is just, so this what I explained here. With if you take that for all of the states, the possible states, even if you take 2, 3 n-dimensional qubit states, then you will get the identity matrix. Okay, so that's what you want to have. 1 here is just the unity, so it means the identity matrix. I showed you how to create the identity matrix. How you get to that. Why you need the identity matrix. This is some more notation. We'll go over that. We talked about the components. The associated bra vector and is the complex conjugate, yeah, in that sense, in that case, with complex numbers. And in row form, we talked about that in detail. And we had that. We have commutators. We briefly talked about operators. So the sequence of operators matters. So how you apply that to your system, it matters sometimes. Sometimes it does not, but more often it does matter. So more often you want to check if what the commutator is. So if it's 0, the order doesn't matter. If it's 1, it matters. Okay. Some more commutator rules, anti-Hermitian operators. All right. So I think for today we can conclude it. Please read through the last slides. This is the notation that we need. We will see how we can leverage the Dirac notation or bracket notation to create operators without needing to deal with vectors and matrices. I will show you how you create operators just by using that simplified notation, symbolic notation. We learned about how to write or different ways of writing down states. So here you have, if you have not only 2, but let's say 100 qubit states, then you want to make sure that you don't have to write 100 numbers per state description. So you find other ways, right? So you could number that from 0 to 100 and make sure that you have 100 down here, so which just says this is 100-dimensional space. Okay. We learned about the inner and outer product. We learned about how to create operators. There will be more, don't worry. This is just a brief introduction. So you'll see this course is a sort of iterative introduction. I will give you some details, something to memorize, something to think about. And the next time we talk about it again, it will be one level deeper. And then again, one level deeper. So it doesn't mean we're done with vectors and matrices. This is everything that gate model quantum computing mathematically is about. We will need to understand better how to create algorithms. We need to understand better how to create transformations. So it will come again, and it will come in more detail. As always, if you have questions, please reach out to me via email or on Blackboard. And yeah, for me, it's Friday. I wish you a nice weekend.